I'm a Group Innovation Funding Manager at Datalogic, that is the entity coordinating Project Rossini. I will be giving you today, I will be presenting you Project Rossini in general, and then I will make a short introduction about the use cases that will be presented by our partners of the project. Rossini is a project funded by EU under the Horizon 2020 program, and it's a project putting together 13 partners coming from different areas. The main objective that we had since the very beginning was to overcome the conflict between safety and efficiency in a human-robot collaboration scenario. And in particular, all the applications, as you will see, are related to the manufacturing industry. From the very beginning, we understood that it was not possible just for one entity to work on a goal that was so big for everyone within the consortium. And this is the reason why we decided to put together different capabilities and skills represented by the partners of the project. All the technologies that you will see today are used in the 3 use cases that are represented by Schindler, IMA, and Whirlpool. In order to reach a goal big as overcome the conflict between safety and efficiency in human-robot collaboration, having on one side traditional robots that are very fast and efficient, but not safe for the operator. On the other side, cobots that are intrinsically safe in the interaction with the operator, but very often they are stopped or not as fast as the traditional robot. We understood that we were forced to work at multiple levels, not only working on the sensing part of the cell and of the environment, but at multiple levels, working, as you will see, at perception level, cognition, and controlling level. In Rossini, in the Rossini project, we did work on the sensing part as Datalogic and together with PILS, developing 3D cameras and a cluster of laser scanner and radar that are basically collecting the information from the field and that are used by the controller, so to allow the system to recreate and to make different actions that are not possible with current technologies. In particular, we are able, through our planner, to give tasks to the human and to the robot in their interaction, changing the task if we see that the operator, for example, is tired or a little bit slow if compared with what scheduled. Apart from that, we have a complete understanding of the scene, and we're putting all together this information with the semantic scene map. Within the project, you will see that also we have worked at actuation level with a robotic arm that has been developed by one of our partners, Subsea. And the human factors that are very often considered only during the first phase of the design of the cell are considered also at while the system is running. So the proposed solutions are related to high performance safety sensors, as said, 3D cameras and a cluster of laser scanner developed by Datalogic and radar that will developed by PILS that will improve the detection and safety condition. We have developed flexible and AI-based algorithm, so to optimize the efficiency of the robot and adapt it to the operator. Job quality parameters will be used also at runtime. This is possible thanks to the high understanding of the scene that we have thanks to our sensor and to the controller that is helping us in doing all these activities. You will see an innovative collaborative by birth robotic manipulator that is deployed in the Schindler use case. At the end of the day, all the technologies that we have developed are used by our use cases. The three use cases cover a large range of human-robot collaboration applications within the manufacturing industry. But many of the technologies are applicable in different fields. Project Rossini is area, so usually area for all the people that are more familiar with funded projects are coordinated by R&D center or universities. In this case, it has been coordinated and led by industrial partners. And the idea from the very beginning was to develop technologies able to solve issues in different problems in different fields. This was the main idea. So also while selecting the use cases, we have worked with entities with different problems or different interaction with the manipulator, the robotic manipulator. If we see the challenges that we face with the project. In the Whirlpool use case, as you will see, we have a continuous flow line working with heavy products at high speed. This is very challenging because you have to consider a high payload on one side, put at a certain height that is dangerous for the operator, and high speed of a continuous flow line. The Schindler use case is more close to the traditional application for cobots. And here the main challenge is the high production variability. The EMA use case has challenges that are very different from what's seen in Whirlpool and Schindler. In this specific use case, we have to manage indoor navigation and the interaction between the robot arms and the operators. So on one side we have the navigation, and on the other one to control multiple arms in a specific area that is shared with multiple operators. I leave the floor now to the three use cases. This presentation is dedicated to them and the solution that have been developed within a project that is close to its natural expiration. It is at the end of this month. So I want to thank Riccardo and all the use cases and welcome again to this presentation about Rossini and the technologies developed for its use cases.
Thank you very much, Matteo. And so now let's start the use cases illustration with Miroslav Vornikak from Whirlpool that will explain us how the Rossini solution has been applied to a domestic appliance assembly line.
Okay, thank you very much. So I'm Miroslav Horničak. I'm from Whirlpool EMEA Corporation, EMEA, and I'm industrial engineer, and I was responsible for Whirlpool use case. As what we will see during our presentation are these few topics, these outlines. So I will explain you our needs and challenges in our use case. So just a little bit more explain our use case, Rossini components, what we are use it in, and how it looks like. So needs and challenges as was presented before. Our use case is with a heavy payload. So on the beginning of the project, we had two different possibilities because we manipulate in more our location with the heavy payload with these concrete counterweights in our products. So we have two, as I said, different. One is a stop and go and continuous flow, and the main goal it is that now in this state the operator needs to manipulate. So take the counterweight from the container, assemble it to the washing units, and fix it. The objective of our project or our use case was improving job quality and at first, okay, the ergonomics of our operators because as was mentioned before, the payload of one counterweight is approximately 14 kg, so it is really heavy and not good for the operator health. What we want to solve during our project and what was the big challenges was this, as I said, it is a heavy payload for the robot because when we calculated the final payload compare with this that we have a 14 kg counterweight and add the weight of the final gripper, because gripper is important part of our use case. It is up to 40 kg, not 14. Respect the takt time test assignation and okay, for recent solution, we foreseen that we will have a robo, so one big arm driven by RS4 system. Maybe okay, our first goal was the standard industrial one, and redefine the way how we will work with this counterweight. So that means when we will replace the hard work of the operator, so we need to redefine the work for the operator as well. So what we want to, what we used during our way or during our mission in our use case was this, that we use it on the beginning, the virtual design tool in our use case to find the right placement of the camera with using the semantic scene map, skeletonization algorithm, and all the testing in virtual world before we finalize our layout. Then the important part of our solution is the RS4 controller, which are take care about or control all our safety aspects, so all our safety tasks, and okay, monitor the distance between the human and the robot. To this RS4 controller is connected to DataLogic 3D safety cameras, which are placed according to our virtual tour in a specific construction to cover all our needs from the dangerous zone and also from the collaborative point of view. Then we, in our use case, we are using also the standard laser scanners. There are three in this case, and these standard laser scanners has two different functionality. First one, it is the cover all our workplace to inform our system that something is inside and to monitor the area. And the second second functionality, it is the stopping in dangerous and forbidden area. As you can see in the picture on the left, we have two red rectangle. In these two rectangle, these scanners working like a safety stop, because in our use case we didn't use the standard physical barriers. Next safety device or next part was developed in our use case. It is a soft skin developed by Pilz. And this soft skin we implemented directly to our gripper, which now we can say that it is collaborative gripper, because we used the FANUC CR35 robot, which is already collaborative, but during the assembly of the counterweight, according to this big payload, we need to turn off this collaborativity function of the FANUC. and we replace this functionality and we put this the safety functionality directly to the gripper, because this gripper is the nearest part close to the operator where we can react for these activities. In the continuous flow mode, we are under the safety speed, okay, under the 250 millimeter per second. So in this case, we can guarantee that also our gripper is with using this soft skin is safe and collaborative. Next part of the Rossini components that we use is WP4 PC, where we have installed the ROS system, and all this pardon. All this system is driven the final motion planner and final execution layer. So that means with the ROS we control all the tasks about the trajectories of the Rossini inputs and non-Rossini inputs, because in our use case we are also using a lot of different inputs which are not connected directly to the safety, like for example the camera system and additional sensors which are control our final tact. As I spoke before, the important part of our use case was the design and developing of the gripper. Here, as you can see here in our in these pictures, the gripper was designed with our partner Vintiv according to the all requirements described in the specification TS15066 about the collaborativity requirements, what must be implemented if you want to say that also this part as a gripper it is safety. So that means, as you can see on the pictures, our gripper doesn't have the sharp edges, and for holding the counterweight, because of the payload, we're using two different gripping systems. One gripping system is the suctions. As you can see here, these three suction cups. These suction cups are related to the taking the counterweights directly from the container, and then when we are above the level of the other counterweights, we go inside the gripper and we finally grip the counterweight by the fingers and hold with the two different gripping system to guarantee that we will during our motion we will not fall down the counterweight. Inside the design of the gripper is also included the human-robot interfaces, as you will see in the next slide, which is contain of which is the different light from the light bar according to the state of the robot or state of the process. As I said before, inside the gripper we have also the camera system. As you can see here, this camera is related to define the final position and correct the position of the counterweight before the assembly inside the washing machine. And soft skin was already I already spoke before about the soft skin, and it is here. Here you can see these human-robot interfaces, and we decided to inform the operator about in which phase of the cycle we are with the different lights, with using the different lights. So then in the final video you will see that how it is working. But as you can see on the left, when the robot is in the state that is waiting for the information from the line, from the other world, and everything is fine, we have launched the blue color, Then when we move inside our danger zone, okay, that means for the gripping, the counterweight and so on, we change the color to the red one. When the robot is prepared and all the safety aspects is in collaborative mode, we change the light for the collaborative. And if we have some case that we have some failure or unexpected stop, we change the color to the yellow one. Also, these we will show you in a next next step in the video. Next things, what is also connected to this human robots interface, it is that we have confirmation button on the gripper, which is also changing the light according to the state where we are. Then we have some light totems in our use case, and also on these totems we show to the operator that in which phase we are. In this slide you can see that how we were working with the semantic scene map and schematization map for define the right work of the human and the robot. This is our final use case. It is installed in our TVOA area, so that means training campus. I can briefly introduce you that the layout. As you can see here, the yellow part, it is 1, 2, and 1 is mounted here on the left corner of the container. Are these standard laser scanners. One Datalogic Safety 3D camera system is on the right corner on the up. Then another one is not really good visible, but it is here after this light, and it is covering our collaborative zone. Our robot is a Fanuc CR35, and here you can see also the gripper. The totems are here, the light bar is here, and also we have another totems connected directly to our safety system. Okay, and now I can show you the videos from our final integration. Just a second. I have some issue with. Okay, maybe I can do it in different way. Okay, now it's working. This is a whole cycle. So now you can see robot is prepared, the blue light is turned on, and we're waiting for the information from the line to start the cycle. The washing machine is moved. When the robot go inside our dangerous zone, so that means our pickup zone of the counterweights, is changing the lights. Me explain now the functionality of this scanner, safety scanner. So when I go inside, as you can see, the robot was stopped. When I go out, the robot can move and finalize the cycle. So it is put it automatically. So we go on, down, turn on the suction system, go up to the safety position.
Ciao.
Ciao.
Posto.
Then when we are in the safety position, we close the gripper. So we are holding in a safe way. This is a stopping driven by the RS4 camera system. Okay. We're going to the mounting position. So now the robot changed the rotation. Camera system find the right coordinates. Are we going to perform the final assembly? We are still in the red, as you can see. Now, when the robot knows that we are in safe, so that means that nobody can touch or put their hand or something like this. You will see we change the light to the green one, as you can see now. Also, the confirmation button is changed. Operator fix and give the information to the robot that you can go out. And now I will stop the system if I want. When I go out, the robot continue to finish the cycle. Okay. And now I want to show you also the functionality of the soft skin. So, as I said, when the robot is in the red, in the green zone, as you can see, okay, when I touch the soft skin, whole system stop and needs to be resetted, and we can continue, and the robot continue to finish the cycle. Okay, the last thing what we need to finalize, it is only some measurement which will be performed this week, and we will continue to finalize the final delivery. Okay, many thanks from me.
Thank you very much, Miroslav. And
You're welcome.
Now it's the turn of Federico Filzi from Schindler that will explain us how the Rossini technology has been applied instead to a different scenario on the electronic components production. Please, Federico, go ahead.
So hello to everybody. I'm Federico Filzi, and I am Schindler, and I'm responsible as the technical part for the Rossini project since the beginning. Just a quick overview to focus on Schindler in terms of to better understand what is the product that we are speaking about. The panel inside the elevator is the focus of the product of which we focus about Rossini. What is the starting point? The starting point was to analyze a product that is made by two different size, front panel size and back panel size, and the different in the two size we have different components. And analyzing the type of product, we decided to find a way to implement a solution, a platform that can be a cooperative solution. The particular of this product is then is a very extreme configurable product by different types of components according to the number of floors, the number of keys that you need to have according to the single application. And so for Rossini to simplify the focus of the demonstration, we focus on a configuration that is, can say, on average a product on with the 8th floor. As approach in the current layout, in general terms, the configuration of the current layout is made by a kitting phase and then an assembly phase. With the Rossini, the objective of the Rossini was to implement a solution in which the kitting part and the assembly part will be together, and with the aim of to improve the job quality and ergonomics, increase efficiency and productivity, and optimize the production lines layout, making a solution that is a new concept in general terms, because it's no more a line with the different steps in the line, so according to the phase of the production for the product, but it is a cell in which the robot and a human operator can work together, eye close, with precision and task assignation, and where the collaborative part made by the robot and the human operator is very linked. The robot and operator, as you can see on the right side, are very close to one another. So to make this step, it was important to analyze all the operation that we need to see a panel and to divide the operation between what can be done by the robot and what can be done by the human operator. And this analysis was done at the beginning and there was also done ongoing in order to define also the equipments and also to verify we have some constraints about the position of some tools or some fixture to related to the product. The robot was, like I say, the part in the middle of the cell, and it was realized by Subsi. And this robot is a completely new one. It's not, is not on the market. Is related to Rossini project itself. And on the robot, we decided to use some equipments that can be useful for the application, such as a screwdriver, gripper by robotic, is an electrical gripper, and according to the division of operations between human operator and the robot, we decided to focus the activity on the robot related to the high repeatability of the components. So we focus on the pick and place of the push button and the plastic face between the shaft material and the screw that is used to fix the pre-assembly frames plus the push button on the shaft material. At the end, the current state of the demo is this one. We have a demonstration which you can see the product in front of the robot, and on the right side we have also a singularize, you can say, divide the nuts on the to be taken by the robot, because the screwdriver, according to the dimension of the nuts, has not the possibility to have a solution, a standardized solution. We have to also to customize the solution with the solution to the dimension of the nuts, that is a M3. And as you can see here in some picture, then I show you also a video. You can see that the cell, the robot has also a touchscreen with some information that is related to the operation that is ongoing, and on the right side you can see also the output of the 3D camera. That is also the other equipment that I will show you right now, that are related to the safety of the human operator, because the platform, as was told before, has to guarantee the best safe situation in this cooperation between the robot and the human operator. So with the support of data logic that is in the consortium, it was developed a new camera that is this one, starting from a 3D virtual concept, and then on the right you can see the final solution. And this camera, with also the activity of iris, was done simulation of the presence of the person in different situation. The human operator was simplified also in the beginning, considering the skeleton of the human operator, and this simulation can see different situation in which can be the people, the human operator near the robot, in order to understand what can be also the behavior of the robot. These are some pictures according to all this journey that was done by Iris, in order to, and also with data logic, in order to understand what can be the schematization of the people. We have also the Frank Rambert as a controller for the application. And then another important point to say is that another contribution by Unimore was to define and realize an algorithm that can understand, according to the movement of the robot and the movement not predictable of the human operator, what can be the trajectory and the behavior of the robot. So the robot has to be adaptive to the behavior of the human operator. So also this part was very interesting, because you have to imagine that some behavior are not so easy to replace. To do, but we have to simulate as much as possible all the situation, and the robot has to change the trajectory according to the what happened and how is the operation that the human operator can do. At the end, I will show you the video that in which you can see what I told before. You can see here the robot that is in the phase in which the robot has already put the push button inside the frame. And in this part of the video, you can see that while the robot is doing this pick and place of the frame, the plastic frame, and the buttons on the shaft material, on the left side you can see the operator that is in the assembly phase of other parts that we have seen that are customized part, or in other case we have a lot of different labels to apply, different also cables to manage, so flat cables to manage and to connect, and so the robot cannot do with the high repeatability this operation. You can see that there are also some activity related to the PCBA in which you have to scan the ID barcode, and then you have to fix on the shaft material, not in a planar way, but you have to adapt it according to the conformity of the PCBA and the pan. Here you can see now the screw driving of the nut. while the operator is working. And as you can see, is the space in which they are operating is very close. On top, you can see in this video, but is there are the two data logic cameras that are looking at the space and the behavior of the operator and the robot. And I can say behind, you can see also you have to imagine that there is also the part of Unimore with material panels and what I told before, according to what is the behavior and the type of unexpected movement that can do the operator. In this case, they are working together without in an unexpected behavior, but is a consolidated part and so on. Okay. So from my side, that's all.
Thank you very much, Federico. So I will leave now the floor to Alessandro Carapia from IMA that will explain instead of our last use case for Rossini, that is in the food production packaging operation. Please, Alessandro, go ahead.
So I am Alessandro Carapia. I am part of the research and innovation department of IMA, and I am responsible for the Rossini project for what concerns the IMA use case. Okay, as in the other use case, this will be the outline of the presentation. So I will go through the needs and challenges. Then I will explain you the Rossini components used this use case, and then finally I will go through the technical features we implemented and we integrated in the IMA use case. So IMA is a world leader in the design and the manufacture of automatic machine for the processing and packaging of pharmaceuticals, cosmetics, tea, and coffee and food in general. In this use case, we focused on tea bag machine. Just think about that 2/3 of the world's tea bags are produced on IMA tea bags machine. So this is a very important machine for IMA. And we focused on the feeding material necessary for these machines, and in particular on the paper reel that are necessary to do the tea bag. So in particular, we have three kinds of paper reels: the filter paper reel, the tag paper reel, and the outer envelope paper reel. The reels are important in the packaging machine in general because this is a shape of feeding material that is not only on tea bag machine, but in general this is a common shape that is present in different kind of machines. So this is of interest because can be applied this use case to different kind of automatic machines. At the moment, at our customer sites, the reels are all loaded manually, and so the idea in this use case is to load the reels using a robotic solution that has to be collaborative because the operator is, by the way, present in the factory and has to perform operations that need for sure a technician that's know very well the automatic machine. The idea is therefore to improve job quality, as I said previously. The work at the moment is done all manually, increasing the efficiency and productivity, and thinking about a scenario with more machines served by only one robotic solution. The idea is to perform different tasks on this kind of machine. That's, for example, are also the carton loading and also the micro stoppages solving, that are very short stops that can happen if something like the carton stuck for some reason related to the environment. For example, for the cardboard, the stacking could happen if the humidity conditions are not the good ones. Okay, so the idea is to perform a speed and separation monitoring in this use case, according of what is explained in the standard ISO TS 15066. In this use case, the most particular thing with respect to the other is the presence of a mobile base, so of an AGV, because as I said previously, the future scenario will be for sure to share this kind of robotic solution that will be a mobile manipulator with multiple machines in order to have a faster return of investment for the customer. So the idea is to monitor the area in order to recognize where is the operator and where is the robot, and to act consequentially. So let's talk about the components of Rossini used in the use case. So for sure, as in the other use case, we used a lot the virtual design tool from Iris. That is a virtual tool necessary to simulate the environment in order to find, for example, the best places for the installation of the sensor. So, for example, in this picture, you can see the 3D model of the automatic machine, the warehouse where the reels are stored, the operator, and the mobile manipulator. These blue cubes are the cameras, and in the image below, you can see the 2D image detected by the cameras. And the idea is to use this kind of tool to check if all the areas are covered well. And also this can be used for testing, for example, the skeletonization algorithm of the semantic Shin map. Another important feature applied in the use case is for sure the Rossini Smart Safe Sensing System, so the so-called RS4. And in particular, in this picture, you can see the controller, RS4 controller. On the left and on the right, you can see the semantic map Shin controller. The RS4 system is responsible to do the speed and separation monitoring. So the operator is detected, the robot is detected, it is evaluated the minimum distance between them, and with this data, the speed of the robot is regulated. So if the distance goes below a predefined threshold, the speed is low down. So in the use case, have been installed 3 data logic cameras at a height of 3.5 meters on aluminum pillars. So here you can see one of them. And the other RS4 sensor installed in this use case is the PILT radar that has been installed in the area of the reloading of the machine to cover better this zone, because in this part the operator and the robot work very closely, so it is important to monitor well this area. In the IMA use case, we use also the cognitive layer and the flexible and the execution layer. For what concerns the flexible execution layer, it is used a lot in the use case, the dynamic planner of the trajectories. So the trajectories are not given through waypoints as a standard robot, but they are computed automatically, so only giving the start point and the final point, and are also given the obstacles of the machine. So for example, in this picture, you can see in green the obstacle represented by, for example, the sphere. And you can see that the trajectory computed avoids the obstacle in order to not have a collision. And this is a very important feature used for all the trajectory we perform in the use case. About the semantic scheme map, in the use case, we apply the skeletonization algorithm, because here the idea is to use the 3D beams of the skeletons in order to do a replanning of the trajectory if, for example, the operator puts, for example, an arm in a zone where the trajectory was planned before. So the robotic arm can avoid the operator computing a new trajectory. Another important component used in IMA was the design tool for human and robot collaboration and the software for the flexible task assignment. So together with the collaboration of TNO, we evaluate the physical load related to the real task, and we see that it is very important in terms of job quality, and taking the data about the duration of the reels and about the ergonomic aspects of the loading position of operator, a rating was established for the different tasks, and through the Rossini task planner, we assigned the task to the robot or to operator using this rating. And it is very important, the task scheduler, because can consider also if the robot is busy, for example, on one machine, can assign the task related to another machine to the operator and vice versa. So again, thinking about a scenario with multiple machines served by a mobile manipulator. How we communicate with the operator through a smartphone app, and because is the easiest way considering the very dynamic environment, and through this app we can communicate to the operator the task to do, the recovery actions for the robot if a failure occurs, and also to confirm the right gripper setup, because the real core of the three kind of reel is not always the same, but there are two kind of diameters, so two kind of fingers on the gripper. Okay, here I will go through the demo technical feature, and then I have a video of the whole demo. So, talking about the mobile manipulator, it is composed, as you can see in the picture, from an AGV, and in this case, Mir 500, and by two robotic arms from Universal Robot. All the integration has been performed by IMA. So it was integrated the AGV together with the two robotic arms. We used on one robotic arm a gripper for the reel loading, and on the other a 3-finger gripper to remove the reel core. We decided also to use this kind of gripper on the other arm, for example, because it will be very useful to test the micro stoppages solving. And there are also cameras. Here you can see HD cameras on the robot to detect with high precision the position of the reels or of the mandrels of the machines. On the mobile manipulator is also installed a tower light, and to let's say visualize the status of the robot, and also to check the safety mode triggered. So the normal speed mode, the reduced speed mode, and the safeguard stop that are triggered by the RS4 controller. So in this picture, you can see the arena where we are testing the different tasks. The 3 cameras from Datalogic and the radar from Pilz. You can see also the real warehouse, the machine, and the mobile manipulator. We performed an important work of integration, because having a mobile manipulator means that we have to set a wireless connection, and the important thing is also to have a safe wireless connection. So we installed an industrial wireless connection in order to communicate from the RS4 controller to the safety part of the mobile manipulator. So in this cabinet, there are all electronic components needed to establish this kind of connection. Last thing very important is that all the components are integrated in the Rossini framework. That means that all is communicated via ROS. So the robotic arms, the AGV, the grippers, and so on. So this brings to, let's say, have a data exchange easier. And for example, as a matter of fact, in this screen, we can visualize all the information coming from the different components. So the cameras, sensors, and so on. So here I have a video of the demo we performed. The first part is related to the human-robot communication. So here there is an example of the tool, the verification of the gripper setup. So if it is the first run of the day, or if the previous reel was different from the requested one, the operator has to look at it. This is a task given to the operator. For example, the preparation of the junction of the reel that at the moment is done manually by the operator. And this is an example of mission assistance needed from the robot. And it is important to see that also the different explanation are given to the operator to recover the situation. Here instead you can see the reel picking with the RS4 monitoring. So here the process is the following one. So the AGV approaches the reel warehouse, and the navigation is done with the arm stationary. So the safety is managed by the AGV. When the AGV arrives to the reel warehouse, by ROS, the AGV triggers the monitoring from the RS4 controller. And so the distance between the operator and the robot is evaluated. So you can see, for example, now that the tower light is green, so the distance is enough to have a full speed mode for the robotic arm. Instead, when the operator approach, the reduce speed mode, as in this case, you can see, is activated, and if they are too close, the safeguard stop is triggered. As I said previously, all the trajectories performed by the robotic arms are evaluated, computed, let's say, with the dynamic planner. So we don't know at the beginning, the operator doesn't know what will be the trajectory performed, because it can change in relation to the obstacles of the scene. You can see in the screen the obstacle given by the reel warehouse that is spawned using the position detected by the cameras. So the virtual obstacle is spawned. Here you saw a human touching robot condition. So the robot goes in a safeguarded stop. And that this is very important feature, because in this situation we avoid a clamping situation between the reel and the perch that's on which lay the reel picked from the operator. So this is a very important feature for what concerns the risk assessment. In this case, you can see another condition of a human touching robot, and the safeguard stop works very well. So after the mobile manipulator picked up the reel, the AGV navigates toward the debug machine, and then, as in the previous case, when the goal is reached, start the monitoring of the RS4 controller, and the robotic arms can start moving. Also in this case, the cameras is used to detect the, for example, the machine, looking at some marker attached on the machine itself. And when the marker is detected in the, let's say, in the virtual scene, it is spawned the 3D model of the machine. and the trajectory can be performed considering the obstacle given by the machine itself. Here you can see a real core removal from the three-finger gripper, and also an important integration work in the use case is done also thanks to the help of the University of Bologna to integrate this technology in the specific mobile manipulator we are using, because we have two arms, so the dynamic planner of Rossini has to be shared between the arms. So in order to have the distance monitoring work for both of them. The reel loading is important because after the reel was loaded, the operator has to perform some actions on it that are the setting of the mechanical lever to verify the level of the reel. So the operator has to move this kind of lever and has to place in the correct position the reel on the mandrel. So now, for example, the reel is loaded. The operator approach at this moment already the reduced speed mode is triggered, and now it's stopped, and the operator can do all the things needed to make the reel workable for the automatic machines. And all the trajectory to come back to the home position are computed with the visual dynamic planner. Just to show you another case, this is the other kind of reel loaded. That is the middle one. We tested it in the IMA use case. And also in this case, I put it into the video because it is interesting as the operator sees that, for example, the reel doesn't go very well in the mandrel in terms of orientation. So our technician go to solve this kind of problem without looking at the behavior of the robot. The robot stop and the problem was solved. So as you can see, the monitoring works very fine. Okay, so this is the monitoring performed by using the cameras from Datalogic. Another sensor we installed is the pulse radar, and also in this case we performed human robot labeling in order to do speed and separation monitoring. So you can see, for example, in the virtual representation, the point cloud of the robots that are moving, and it is depicted also the center point of the point cloud with a pink cube for the robot. Instead, for the human operator, it is used a blue sphere. So you can see that the human robot labeling is performed well. So also in this case, we can use the data of the distance and of the direction of movement to perform a speed and separation monitoring. It is not, I don't put it into the video, but we also tested the trajectory scaling algorithm developed by Unimore that take in consideration not only the distance between the operator and the human, but also the direction of movement. So we can slow down the robot only if operator and robot comes toward each other. And in this case, the speed of the task increased because there are less stop of the robot. Finally, this is an example of the skeletonization performed by the semantic scheme map for the IMA use case. Thank you so much. I thank you for attending the meeting and for the attention.